Welcome back to Blockstream Talk. Today we're speaking with Andrew Poelstra. In his role as head of research at Blockstream, Andrew oversees a number of projects that I think many of us in Bitcoin are probably only peripherally aware of, but that Andrew and his team have been working on and thinking about for years already. In this conversation, we talked about Miniscript and a possible deployment on Jade, a review of Simplicity. If you're interested in that, don't forget to also go back and look at Blockstream Talk number 26, where we did a deep dive on Simplicity. Drivechains and how they're different from layer 2s like Lightning and Liquid, Bulletproofs++, Frost and Musig 2, and also how paper computers can be used to secure electronic computers. Andrew and I discussed this idea about a year ago, how paper computers can be used to generate, encode, and even recover Bitcoin's secret keys. At the time, I thought it was pretty cool, but since then, the recently launched Codex32 book, which has a number of punch-out paper computers inside, is also really well presented from an aesthetic perspective, and I think the paper computers look really cool. So be sure to check that out. I think the book should be out on the Blockstream Store by the time you see this, so have a look. If it's out, we'll put a link in the description below. Andrew, good to see you again.
Hey, good to see you too.
Can we start maybe with a quick introduction to yourself and Blockstream Research?
Yeah, for sure. So I'm Andrew Poelstra. I am the director of Blockstream Research, which I have been doing since the beginning of 2018 when our CTO, Greg Maxwell, stepped down and we restructured our engineering department a little bit to have a distinct engineering and research teams. So my team now has, I think, 8 or 9 people. We sort of split, even within research, we kind of split into 2 teams. One half who does cryptography, zero knowledge proofs, signatures, stuff like that. And the other half who does scripting focused stuff. And that's Miniscript, Simplicity, things like cryptographic derivatives and options and applications of these scripting schemes, of smart contracts on top of Liquid. And in some ways outside of Liquid, we try to be a little bit more... We try to be Bitcoin focused where we can, although certainly having a multi-asset platform like Liquid and one with all sorts of crypto toys makes it a good fit for a lot of what we do. On the crypto side, we have Jonas Nick and Tim Ruffing and Liam Egan now, who joined us recently. He's the author of the Bulletproof++ paper, which is an extension of a zero-knowledge proof scheme called Bulletproofs that we developed in part at Blockstream Research a few years ago. So Tim and Jonas have been with us since I think before Blockstream Research was a thing. They've been instrumental in pushing forward Musig and Frost are 2 big kind of crypto things. Musig is an interactive multi-signature scheme, and Frost is an interactive threshold signature scheme. So the difference is with Musig, you can split a signing key into maybe like 5 parts or whatever, and then if all the participants come together, they can interactively produce a signature. With Frost, you can have a threshold. So you can say like any 3 of the 5 participants can come together. Since Liam joined the team, we've also branched out a bit and we've been working on zero knowledge proofs, in particular Bulletproofs++, as I mentioned. So we've got an implementation of that in C that we're hoping to eventually bring into Liquid. We've got one in Rust, which we're using in some ways as a reference implementation. And we're also working on cleaning up the Bulletproof++ paper, trying to simplify it where we can, trying to get it into a state where it's easy to understand, even though it's in some ways a fairly complicated thing. Then on the scripting side, we've got myself, I guess. I would consider myself more on the scripting side than the crypto side. Then we have Russell O'Connor, who has been with the company almost since its founding. He's been working on a smart contracting language called Simplicity for the last many years. And he's kind of like the force behind Simplicity. In the last couple of years, more people in the team have joined, and we've started to make this much more of a team effort and start working towards deployment and working on to making this real. But for the many years before that, Russell was writing code. He was writing papers. He was publishing stuff and working out all of the detailed mathematical structure of everything. Joining him is Sanket Kanjelkar, who is a co-inventor of Miniscript, which is another project that came out of Blockstream Research. So Miniscript is a way of reasoning about Bitcoin script in a way where you can model the script as kind of a set of spending conditions, as a set of keys that you need to sign with, as a set of hashes whose pre-images you need to reveal, as a set of time locks, time conditions. So your coins need to be a certain height before they can be spent, and arbitrary combinations of these. So you can have some set of keys, then after a certain time, a different set of keys comes into play, kind of stuff like that. Prior to Miniscript, it was possible but quite difficult to do these kind of things in Bitcoin script, because the model by which Bitcoin script operates is kind of one where you have all of these opaque blobs of data that are all on what's called a stack, one after the other. And you have this script engine, which is just running opcodes to rearrange things from the stack, to pull things off the stack, to put things on the stack. And then sometimes, under certain conditions, it will interpret some items as public keys and signatures and hashes and pre-images and stuff like that. But in the course of the script interpreter running, you don't really, this data doesn't really have an identity until the last possible moment. It's really just this opaque blob manipulation machine. So Miniscript allows us to reason about stuff not as a sequence of blob manipulations, but as a set of spending conditions, which allows us to do all sorts of analysis in a much cleaner way, and also to make the user experience of using this much cleaner. So Miniscript and Simplicity are kind of the two major projects that we work on. Miniscript being a subset of script, which just works on which works on Bitcoin today. Simplicity being a much more ambitious, complete overhaul. So that's myself, Russell Sankit, and also Christian Leva is our fourth member of the team working on the Simplicity front. And we're all kind of doing different things here, where Russell, of course, is working on the core, consensus code, the C code, the logic there. Chris is working on some of the wallet structure and the tooling around being able to actually use Simplicity, at least in a kind of playground context. Sankit is working on example programs and making the language itself a little bit more accessible. And then I kind of write blog posts more or less and try to keep everything together. So beyond that, and then we have two more people on the team who are kind of just like free agents, I guess. We have Andrew Chow, who's a Bitcoin Core developer. We sponsor his work on Core, and in particular, he is the Bitcoin Core wallet maintainer. So he's been an incredible force on all sorts of wallet protocols, including output descriptors, PSBT, the shift within Core from using the moving towards SQLite database rather than the old BDB database, which was a little bit of I don't want to say unmaintained, but we were using an unmaintained version of it, and it was certainly showing its age. SQLite is a much nicer thing to work with, and the combination of SQLite and descriptors has meant that the entire architecture of the Bitcoin Core wallet has been radically transformed in the last 5 years, largely because of Andrew's efforts. And it's in much better shape than it was before. So just as an example of the kind of problems that we used to have before. In the original wallet, kind of as conceived by Satoshi, the wallet would keep track of signing keys, right? So you have a public key that anybody can see on the blockchain and use to validate signatures. You have a secret key, which you use to produce signatures. And in the early days of Bitcoin, an address and a key were kind of the same thing, right? Like you think of an address as just an encoding of a key. But as things have evolved, there were kind of new address types that appeared. So initially we had these pay to pub key hash addresses, where the address, rather than having the key, would actually have a hash of the key. And then later we had pay to script hash, which would allow you to do multi-signatures and multiple key kind of things, also hidden by a single hash. We had SegWit, which then introduced a couple new address formats, a new Best32 address format, and a new way of treating public keys, where the public key would be part of the transaction output, but the signature, rather than being directly inside of the transaction input, would be in this new witness field of the transaction. It was moved out of the way in a way that allowed the hashing structure of transactions to change. And then Taproot, of course, the latest version of SegWit. So all of these different script output types use the same keys. I guess Taproot actually uses a new kind of key. But we had the same kind of key that could now correspond to multiple address types. And Bitcoin Core 5 years ago didn't really distinguish very well between these. So for example, if somebody generated a SegWit address and gave that to you, you could take their SegWit address you could reinterpret it as a legacy pre-SegWit address and send coins to that, and the wallet would receive it. And it wouldn't, like, the user had no ability to control this, to say, like, really, I want a SegWit address, like, because the address identifies payments to you. And so if you give an address to someone, you want the coins to go to that address. You don't want them to change the address, send money to a completely unrelated address from a user perspective, and then still have your wallet acknowledge the coins. This is going to mess up your accounting, right? It's not. So this descriptor project that Peter Wolla and then later Andrew Chow and myself and Sankit joined in on. This descriptor project allowed us to separate all of these things. And the Miniscript allowed us to generalize it from more than just one key to, as I said, multiple keys, hash pre-images, time locks, arbitrary combinations of these kind of thing. And then the final person on our team is the last, but certainly not the least, of course, is Kiara Bickers, who is the research communications. She's in charge of communication inside and also outside of the research department. So internally, that means she's working on wiki pages. It means she's talking to people from other departments and asking what it is that they think that we do, and does that correspond to what we're actually doing? And what are people interested in? What are people confused about? What do people want to know? What kind of things are we doing that just nobody's aware of, kind of stuff. And research, as we might talk about and have kind of hinted at, we're doing a whole ton of different things. And often, until we got Kiara on the team, we would find ourselves doing things and realize that no one else in the company was even aware that we were doing it.
Let alone the rest of the world.
Exactly. So the other part of her job is to manage our external communications. So she's written a good number of our blog posts, and the ones that she doesn't write, she's on top of us, like saying, you need to write a blog post about this or write a blog post about that. Or, what are you doing? And like, how does it affect the world? And how can you share that with the world, kind of thing. And I mean, before Kiara, we kind of wouldn't ask ourselves those questions often enough. And so often, in fact, for a number of years, you see almost no public output from Blockstream Research. Other than our appearances at conferences that were almost accidental, right? Like, it was just us going to conferences to meet collaborators and friends, and then, I guess I'll do a talk while the cameras are here, kind of thing. But we didn't have an organized way to do things until Kiara joined the team. And as a final credit to Kiara, so this is what we'll probably be talking about a little bit. We have this new book called Codex32 out. Kiara coordinated all of the typesetting and artwork and stuff. So she didn't draw this, but she found artists for this. And she spent a lot of time with me going over PDF drafts and laying out pages and getting all of these nice drop caps that you probably can't tell on the camera, but they're very nicely illustrated drop caps.
Yeah, no, I can see that. Yeah.
There's a few other illustrations here and stuff that she said, over and over, we need illustrations. So this is really like quite here's a crypto steel picture there that we drew in there.
Yeah. I've got one of those.
So much of the way that this came together and all right. So much of the way that this book came together was Kiara driving forward the human side of this. So it wasn't just a textbook of mathematics. And surprisingly, maybe it shouldn't be surprising, but even for us on the inside, for the people working on developing this and writing it out, it's actually been amazingly more interesting and engaging and fun to use this stuff, having all of the artwork in place and having the new names for stuff where, we don't talk about like multiplication, we talk about fusion, right? And there's various other names for mathematical operations that we had to come up with so that we could tell a nice narrative about what it is that people are doing with this book. And that bringing that narrative together, I think, really improved the user experience.
Oh, that's great. Yeah, Kiara is on our list of people we got to get on the show. So looking forward to having her on and talking to her about everything you guys do. That's a massive amount of work. And speaking of, the book and some of the stuff that you've been working on, that reminds me of last year when we spoke. One of the cool things that we talked about was the idea of paper computers, which was super interesting. So can you give us introduction to that?
So the last year when we spoke, we might have had some paper computers that kind of looked like this. You can see I don't remember if I had them on the show. Let me show you real quick what they look like today, thanks in large part to Kiara's efforts.
Oh, wow.
Here's the same.
Oh, that's cool.
Right. This one, This one's cool. This is double-sided. This was an incredible innovation. The idea that we could fit two computations onto one and then use this double-sided. So in fact, the way that you use this is you turn it while looking at this side. And if you want, like, you can use this for, like, you know, ciphers or stuff. If you're like maybe you're like a student trying to hide stuff from your teachers in grade 4 or something, you could use this. You think of my secret key is going to be a symbol. Let's turn it to like the cent symbol there up top. Okay. There we go. I turn it there, I flip it over, and now you can see this is mapping letters to letters, or letters and numbers to letters and numbers. So you can use that as a cipher. You just map follow the arrows outward to encrypt, follow the arrows inward to decrypt, kind of thing. And you can do all sorts of fun stuff with that. But I'm getting ahead of myself. So let's talk a little bit about paper computers and you know, what are these for? Why would anybody want to use paper computers? So on a high level, what you can do with these paper computers in conjunction with these, here they are before they're cut out, by the way.
So what is that book? Is that the book you just showed that Kiara helped put together?
Yes, this is the book that I just showed. So these paper computers, here's a double-sided one. You see, you cut it out and fold it and stuff. So this book kind of has 3 parts. So one is the exposition that I showed you, kind of explaining what's going on. And then the last part is the paper computers you cut out. And in the middle, we've got a whole bunch of these worksheets. And so the idea is that using these worksheets in conjunction with paper computers, following the instructions that are written out in a fair bit of detail, you can create secret data. So like, for example, seed words that you're familiar with for your Bitcoin wallet. Those seed words, you normally put that into a wallet, and then the wallet is able to derive a sequence of addresses from that. So we have a different format for the seed words that you're able to generate just by rolling dice and then there's a certain worksheet that will help you eliminate any dice caused by manufacturing issues. So what you can do is generate this seed data by rolling dice. You can attach a checksum to it, which is some extra redundant data that you stick on the end, which will allow you to detect and correct errors. So we have a checksum that will allow you to correct up to 4 errors. So if you make up to 4 errors anywhere in your data, then you will actually be able to determine where those errors are, even if you didn't know, and figure out what the correct values were. And if you know where the errors are, which is maybe a more likely scenario, if you have stuff in a crypto steel and then like some of the tiles get worn out or, you know, warped or something like that, you know where they are, then you can correct up to 8. Is a cool thing. And these are guarantees. So what this means is that if you have up to 8 errors, you can determine that something's wrong, guaranteed. If you know where they are, you can even correct them. And if you don't know where they are, you can correct up to 4, which is a nice property. But this is kind of a general property of error correcting codes. So Best32 addresses, Taproot addresses, SegWit addresses have the same kind of principle. And in fact, you can use the worksheets in this book, if you tweak them a little bit, to verify the validity of SegWit addresses if you want. It's exactly the same.
What's the title of that book and how do people get it?
The title of this book is Codex32. There are 2 places to get it. One is the Blockstream Store, which is store.blockstream.com. You can buy this nice, wonderfully printed and bound one that has all these worksheets or tear outs. The paper computers are on heavy paper, and you can tear those out as well. And the other place is to go either to our website, secretcodex32.com, or to the GitHub repo, which is github.com/Blockstream Research/Codex32. And on either the website or the GitHub repo, you can just go ahead and download that. You can print out new extra copies as a worksheet. You can print new copies of the paper computers. You probably want to take it to like a real print shop because it's nice to have them a little bit big and on heavy paper and stuff like that. You can print the whole book. It's all open source. It's all freely available. But like, you know, you definitely want to buy one of these, at least just to have it, because it's such a nicely bound thing. And in fact, I would even suggest that if you buy a copy, you shouldn't actually tear it out and like cut out the parts that come with the book. You should just print your own and keep the book in.
Get 2. Buy 2 copies.
Exactly.
Well presented too. I mean, it just looks really aesthetically very nice.
Right. Yeah, I'm really surprised at like what a piece of art it turned out to be, right? Because the progression here, of course, was that initially we just had these paper computers and then they were kind of boring. They were flat and white. And we thought, well, why don't we put some artwork on them? And then why don't we put some color artwork? And then from there, it just kind of grew to like the artwork is more than just like a decoration on this. You know, the artwork like really visually guides you as to like which of these does what. And it fits into a broader theme about kind of the somewhat magical thing that we're doing here by doing this error correction. And then, as I'll say in a moment, the ability to split and reconstruct secret data, which is something called Shamir secret sharing.
Yeah, let's talk about that. Can you talk a little bit more about Shamir secret sharing and why why people should learn about that?
Sure. So the idea behind Shamir secret sharing is that if you have some piece of data, some reasonably short secret piece of data, so like a Bitcoin seed, then you can split this up into multiple pieces that will allow you to reconstruct it. And so why would you do this? Well, if you have something like a Bitcoin seed, there's inherently a trade-off that you have to make, where if you want your data to be resistant, if you want it to be accessible, right? If you want to not lose it and to be able to recover it, you kind of want to make it pretty accessible. So here's, by the way, like this is a crypto steel tube. Let me just unscrew this and show off for people who aren't familiar. There's all these tiles here with data.
I haven't seen that either. I mean, you've got lots of little... where do we get that? Where's that from? Like I've got the Blockstream metal, but that's something new?
I think these are on the Blockstream Store as well. The Blockstream sent me one. So I assume, I'm going to be honest, people just send me a lot of stuff.
You've got lots of really cool toys.
These tubes are really great. Actually, I got a demo one, I think, from the Blockstream Store, and then I went and bought another like 5 or 6 of them. Because I think this is the way to go for crypto steel kind of stuff. But there's a trade-off, right? So I can have this here. It's all nice. It's just sitting on my desk and like I'm showing it off on podcasts and stuff. But all right, so that's easy. I'm not going to lose it. It's sitting beside my computer. But the trade-off, of course, is that if it's easy for me to access, it's easy for anybody to access. So I have to worry, are people going to come into my home? Are they going to steal this? Is it going to be a target somehow? And maybe I would want to go further. Maybe I'd want to have more than one copy, right? So I have my copy here that anybody can take. If I really want to protect it against like a natural disaster or something, then I would probably want to have another copy that's somewhere else that I can't even keep an eye on it kind of thing. So there's this trade-off here where I can either make this really accessible and redundant and then increase the risk of theft, or I can make it not very accessible and not very redundant and increase the risk that I'm going to lose it. Okay, and that's a trade-off. That's just a trade-off that you have to make when you're storing secret data like this. And so Shamir secret sharing lets you make this trade-off in a bit of a more nuanced way, where it lets you split your data into multiple pieces, and you can set a threshold, typically 2 or 3. And if you have fewer pieces than the threshold, you don't learn anything about the secret. But if you have threshold many pieces, then you learn the whole secret. So it's not like I'm splitting it into like multiple pieces and spreading them everywhere. Like, as the more you collect, the more you know about the secret kind of thing. There's actually this like sharp cliff here where you go from knowing nothing at all, as you get 1, 2 shares, and then you get the third one, and then you know the whole thing. It's the way that this works. And so this lets you kind of do this nice trade-off where if you want to have something that's very, redundant and resistant to people losing shares and stuff, you can create a whole bunch of these different shares. But if you're worried about them being compromised, you can increase the threshold. So what you might do, for example, is a 2 of 3 or a 3 of 5 maybe is kind of a threshold that I would recommend. So you have 5 different tubes that are all floating around the world, being held by trusted friends and family and lawyers and so forth. And any 3 of them will let you reconstruct the secret. So you can lose up to 2 of them and still be able to recover your secret. And hopefully you'll notice when one goes missing and you got to like redo things, right? You can lose up to 2, and you can have up to 2 get compromised. And in either case, you're still fine. And again, hopefully you notice a compromise, although that might be harder to notice, right? It's like somebody is just rifling through stuff. So you can put tamper-proof stickers on these and get some sort of hint that they've been accessed. So 3 of 5 gives you this nice benefit where you have a bunch of tubes distributed, but you need 3 to be compromised in order for your coins to be stolen, or you need 3 to be lost before you actually lose them. So you have like quite a bit of room to make mistakes here. So this is a way basically when you're storing backups of data, Shamir secret sharing gives you a way to distribute that backup in a more nuanced way. And I should say a little bit about how this compares to multi-signatures. because people use multisig in Bitcoin to much the same effect, right? Because the coins in Bitcoin are not necessarily held by a single key. They can be held by as many keys as you want. So rather than having a single key that's split in 3 of 5, maybe I want a multi-signature where I have 5 keys and any 3 of them can sign. And I would say that if you have a choice between those two mechanisms, you always want to use multi-sigs, right? Like multi-sigs are just like universally better. And the reason is that with a multi-signature, you don't need to bring the pieces together to produce a signature, right? With Shamir secret sharing, you've got all these shards. And then when you want the original secret, you have to bring the shards together, reassemble them, put them into a Bitcoin wallet, and spend your coins. With multi-sig, if you don't, you can produce part of your signature with one wallet, part of your signature with another wallet, part of your signature with another wallet, and they don't ever need to, you never need to bring secret data all into one place.
Why is that better?
It's actually not, it's a little bit more complicated to use, which is the reason that you wouldn't use it. The reason that it's better from a security perspective is that you don't have all your secrets in one place. So the idea is that if you're using a multi-signature, rather than you like personally producing part of a signature in one place and then part in another, you might just call a friend of yours who's holding the other key and ask them to do the signature kind of part. And they'll recognize your voice, or maybe have some sort of password because you're worried about deep fakes now, because it's not 2020 anymore. The idea here is that you can add additional access control. So basically, with Shamir secret sharing, in order to use it, you need to reconstruct the whole secret. So at the time of use, the benefit of sharding goes away. That's the trade-off that you're making. Whereas with a multi-signature, everything stays sharded, always at the same time. So maybe a good way to think about this, which I think we wrote in the book, is that you can use a multi-signature to define a signing policy. To say, well, I have these 3 different custodians or whoever, and they could be me at different times, but 5 different custodians, and I want any 3 of them to be able to move the coins. That's a multi-signature. Whereas Shamir secret sharing, you would use just as a backup management. So I've got some seed that I want to keep at rest for many years or many decades or something. And when I want to actually use a seed, I'm going to have to unshard and like undo my security. But as long as they're going to be at rest for a long period of time, and I don't really want to think about them, then Shamir secret sharing lets me do that.
Okay, very cool. Shifting gears here slightly to the Jade wallet. What sort of steps does Jade take to mitigate the dangers presented by electronic computers when storing the seeds long term?
Yeah, so this is the Jade, by the way, one of my many props here.
Yeah.
So I'll talk a bit about some of the issues that people have with electronic computers and why they might want to use paper ones, which we haven't yet dived into. But one of the specific ways that hardware wallets or any electronic computer can cause problems for you is that the hardware wallet can leak your secret key or leak part of your secret key through the signatures that it generates. And there are a couple different ways that this can happen. So one is something called a side channel attack, where during the signing process, you plug your Jade in, right? You produce a signature, or I think you can use it in an air-gapped way. I never have. You plug in your Jade, you're producing a signature, and maybe there's some malware on your computer that's watching your USB bus. And it sees a power draw from a USB bus going up and down very quickly as it's doing various computations. If the Jade were naively programmed to produce these signatures, you might actually be able to distinguish 0 bits from 1 bits in your secret key by looking at the power draw changing, or looking at how the timing changes, or looking at various things like that. These are called side channels. So the Jade prevents against that by using the libsecp256k1 crypto library, the cryptography library, which is what's used in Bitcoin Core and is probably the most widely used cryptography library in the Bitcoin space at this point. And libsecp has a tremendous amount of quality assurance work going into it. We look at the assembler output. So for one thing, all of the algorithms that are in libsecp are written to be constant time. So they never branch on secret data. They never put secret data into array indices. There are a number of things they do to be what's called constant time, meaning that no matter what the secret data is, it's actually doing the same operations. And then even beyond writing the code in that way, we look at the assembler output for popular compilers and for popular processors. and make sure that the compiler hasn't undermined us and said like, oh, I see what you're doing, I'm going to stick a branch in there kind of thing, which compilers love to do because in a compiler writer's mind, compiler benchmarks are the most important value in the world, even more important than security or correctness or anything. It's very frustrating. And CPU designers are in some ways just as bad, right? Your CPU will take different amounts of time to multiply different numbers and things like this. So there's a lot of protections there. Another category though, so even assuming that you have side channels, like your wallet is not leaking data, bias operations through side channels, it turns out that in the signature that it outputs, it's possible for the hardware wallet to leak information about your secret key. So the way that it does this is or the way that you could leak secret data, the way that you produce a signature, first of all, is basically you produce another random ephemeral key, and you mix your real key with the ephemeral key, and that's what your signature is. And you mix it in a way that's dependent on the exact transaction that you're signing. And what's important is that the ephemeral key be unique and uniformly random. So you could leak your secret key just by like copying the secret key and using it twice instead of generating a uniformly random one. And this would be very visible because like part of your signature would look like your public key kind of thing. So to avoid that, the Jade and pretty much any hardware wallet that exists in Bitcoin will use either what's called deterministic randomness. Well, it will for single signature. It uses deterministic randomness, where it will take your secret key, it'll take some message, it'll take some other kind of noise that it has, feed this all into a hash function, and then produce a uniformly random nonce. We call it a uniformly random ephemeral key to prevent those kind of attacks. Now, what's scary here, similar with the side channel thing, is that this isn't observable if a hardware wallet were to do this kind of attack. So I'm telling you that Jade does this deterministically, and it will always be uniformly random and independent. But there's no way for you to tell whether the output is actually uniformly random, right? Like even if you were to load the secret key data onto another computer, and then you can solve out the signature and see what went into it. If this data is supposed to be uniformly random, it just looks like random data. And there's no way you would be able to tell if it was actually honestly random or if it was biased in some, well, you could detect bias given enough signatures. But imagine it was biased in a way that you needed another key to detect the bias. So there's ways where like a malicious manufacturer or like a rogue employee could produce nonces where you attach some bias and then you mix it with a public key that the attacker controls in such a way that the attacker can then undo the mixing and get the bias and then use that bias to extract your secret key, but nobody else can. It's just completely undetectable. So what the Jade does to prevent this, and a few other hardware wallets have started doing this as well, is it uses a technology called anti-exfil. And what this does is it takes some randomness from the computer. It takes it makes its own uniformly random nonce. It shows this to the computer. The computer provides some extra randomness. It then mixes the computer's randomness into the randomness that comes from the Jade. And then it demonstrates, it provides kind of a certificate to the computer showing that it did this correctly. And then the new re-randomized nonce is what actually goes in the blockchain. And what this means is that if you have an attacker who compromised the Jade somehow and is producing bad nonces from the Jade, well, the Jade produces this bad nonce, the computer will re-randomize it. And if the same attacker hasn't compromised your computer, then whatever bias the attacker stuck in there is erased. So in order for this kind of attack to work with anti-exfil, you need your hardware device and your host computer to be simultaneously compromised by the same actor. And in fact, you need a little bit more than that. You need the same actor to also somehow have ability to see the correspondence between your computer and the Jade, basically. So you can't, I guess if they cooperate, it would be tough. But if they were to cooperate, you can maybe sneak some data into the actual nonce that goes out. Although the way that we structure this commitment makes that pretty expensive to do. So the idea is without anti-exfil, the Jade produces signatures, and the signatures that go on the blockchain might leak your key data. And there's actually been a couple high-profile papers where bad wallets were doing this by Joachim Breitner and Nadia Henninger, I believe are their names, are a couple researchers who have made a hobby of publishing papers in which they extract Bitcoin keys from the blockchain by just applying what they call lattice methods to detect biased nonces that are not uniformly random and independent. And what they find invariably is that the compromised nonces are used in coins that have already been taken. So like there are real attacks out there that have been executed and people have lost coins because of it, is the idea. So anti-exfil just like pretty much completely blocks that.
So you mentioned Miniscript earlier. Is there a plan to bring Miniscript to Jade?
I think that there is, but I'm going to be honest, I don't know what the plan is. I'm not the guy to ask.
Well, okay. What would that mean for Jade?
Yeah, that's a great question. So actually, there is a hardware wallet, the Ledger, which has Miniscript on it. See all these, and then I think that Coldcard and Trezor, I've got my Trezor's not open, and Jade are all planning to kind of join in. And what Miniscript gets you on a hardware wallet is it allows you to have a policy, have multiple keys, and put these into some sort of policy. So, for example, you could say, I want my coins, rather than being controlled just by like a single Jade, I want it to be controlled by a 2 of 3 of 3 different hardware devices. I could have a Jade and a Coldcard and a Ledger all together. And after a certain time lock, so if the coins haven't moved in 6 months or something, then I want it to go to a backup key, which is on a Trezor, just because I'm trying to use everything in this example. And what Miniscript gets you is the ability to describe that policy in a universal way that all these different hardware wallets will understand, in a way that they're all able to show the user, these are the different keys, and these are the conditions under which the coins can move, given these keys. Like these keys need to sign, or some time needs to pass, and this other key needs to sign, basically. So prior to Miniscript, you more or less couldn't do that. So the various hardware vendors would support a basic form of multi-signature, which they kind of came to like a gentleman's agreement on. This is the simplest way that we can interoperate. And we're going to support multi-signatures like this. But as soon as you wanted to do something more interesting, as soon as you wanted to stick time locks onto this or do anything more complicated, then each hardware wallet vendor had to choose what exact policies they wanted to support. They had to write a whole bunch of code to produce addresses from this, to describe it to the user, to produce signatures, to do fee estimation, and so on and so forth. And then all that special code that they wrote would only work on their product. It wouldn't be able to be carried forward to other things. And so to interoperate, you needed multiple vendors to agree on specifically the policy that you wanted to do. And so it's just really like pretty much nobody did anything at all, because the barriers to doing anything more interesting than single SIGs and multi-SIGs were so high. So Miniscript gives us universal language to describe arbitrary policies that can include multiple keys from multiple devices and arbitrary combinations. And it also structures this in a way that it's feasible for wallets to show this to users. Although the Ledger does kind of a thing where it will show like a 500 character policy and it will like scroll by on that tiny screen.
Yeah, the screen is too small on the Ledger.
So there's an ongoing project amongst various hardware vendors to try to come up with some like shorthands or some templates and stuff for this, so that you can get away with having a smaller screen. Because I mean the Jade's bigger, but it's not a whole lot better.
Yeah, it feels more readable though. I like the screen size.
Yeah. I agree. So yeah, there's a Miniscript with this very little work from the person creating the policy, it lets you describe kind of arbitrary policies. And for a hardware vendor, you got to put a bunch of work into supporting Miniscript. But then once you've done that, it supports everything, and it will support everything alongside all the other vendors. So you get this interoperability and a lot more freedom than what you could have before.
We recently talked to Christian about Simplicity, and he made some comparisons to Miniscript. What is happening in Simplicity at the moment? And when can we expect to see it on Liquid?
So seeing it on Liquid, that's kind of a fun question. And there's a bit of a happy hiccup in our scheduling here, which is that probably not now, but by the time this is published, I'm going to be a father, which means that I'm going to take a few months.
Congratulations.
Come back and gradually come back in.
That's awesome.
Thank you. So that's very exciting for me. But it's less exciting for the Simplicity team, who now has their schedule kind of thrown out because I'm going to jump off. But the plan with Simplicity is that we are looking to bring together kind of a developer release of Simplicity. So we're going to launch it on the Liquid test network, which is much easier than launching it on Liquid for real. Eventually, we will move it to Liquid. But initially, we're going to launch it on the Liquid test network. We're going to release some Simplicity libraries. release, you can actually see our development live on GitHub if you want, where we have an encoding of simplicity in like a normal text ASCII format with comments and syntax highlighting and all that good stuff. We will have some example programs and documentation stuff that people need to get started. And we'll have kind of an experimental or toy wallet that users can use with the Liquid test network, where they can write simplicity programs, produce addresses from that, and then send and receive coins. So you'll have kind of a playground. With all of these different components together, we'll build kind of a playground where you can actually start using simplicity and seeing what it's like to create programs that do interesting things, and see what it's like to use them. So the idea, and maybe we should reorder this, but the idea behind simplicity and the way it relates to Miniscript is that Miniscript, as I mentioned, lets you do signature checks, hash checks, and time locks. Those three things, and then various combinations of those. We have something called combinators, where you can have an and of those, so both need to be true, or an or, one of them does, or a threshold, you can do 3 of 5 or 5 of 10, or whatever. And the idea is that you can kind of build arbitrary spending policies by building these arbitrary trees, where at the leaves you've got these actual checks, and then you've got ands and ors building all the internal nodes. And so simplicity takes this concept of having a tree-based program where everything is kind of built out of a tree of combinators, and it takes it to the extreme in two ways. One is that the leaves, rather than being like very high-level kind of nebulous things like signature checks, which is actually shorthand for all sorts of elliptic curve math and like something pretty complicated, or hash checks, which are similarly a pretty complicated bundle of things, or time locks, which involve reference to the blockchain. And actually, there's a fair bit of complexity in defining precisely what a time lock is. Simplicity says, well, let's make the leaves be the simplest possible thing that we can still produce programs from, like in like the abstract computer science sense. And the two leaves, there are two leaf combinators in simplicity, that in core simplicity, I should say. And let me grab real quick. Lots of props. So simplicity itself is actually so small that it fits on this t-shirt.
Yeah, I've got the shirt.
Yeah, so this is all like pretty abstract and kind of difficult to read. But what I want to emphasize is that there are two combinators called unit and idem there. Unit does nothing. It just produces an empty value. And idem is the identity function. It takes a value and it outputs the same value. And it turns out that using those two functions and just composing them in various ways, you can actually build any arbitrary computation, which is kind of a cool, surprising thing. And to do that, I mean, you need more than those two. And the other direction that simplicity goes further than Miniscript is that the combinators, rather than being ands and ors of these things, are slightly more mathematically nuanced. So they define ways to take these units and these identity functions and build up arbitrary code from them. But the cool thing is that there's only 7 of them. And all of these are, as mathematical functions, very small. They're all like one-liners, the kind of thing that you can write out. I mean, well, you can fit them on a t-shirt. So what that means is that simplicity, the definition of simplicity, you can fit into any sort of theorem-proving apparatus, so that you can use what's called formal methods with simplicity. So we have a reference implementation of simplicity in the Coq theorem-proving assistant. But if you want to use, Agda or Idris or F# or, whatever other theorem-proving setup that maybe people are familiar with, you can implement simplicity in there. And then you can create formal proofs of properties of your simplicity program. So unlike in Miniscript, where you can argue things, you can kind of convince yourself of semantic properties. You can take a Miniscript and say, well, I'm a countersigner, meaning that there's no way to spend coins from this Miniscript unless I am the one signing it. And you can make statements like that, but they're all kind of, the argument for it is rigorous, but it's kind of ad hoc. And it's a little bit informal because ultimately Miniscript is only as well defined as a script interpreter that's underlying it, right? So every fragment of Miniscript is something like a checksig, which means you take a key and then you call the checksig operator. And the checksig operator is defined by the C++ code in Bitcoin Core. And it has like all sorts of, C++ is very difficult to really nail down exactly under every edge case what the code is going to do. In simplicity, well, sorry, in Miniscript, you just can't load that. You can't create a formal model of this. So you're kind of doomed to be doing this kind of ad hoc kind of reasoning. And the danger there is that if you try to scale Miniscript up to do more complicated things, imagine Bitcoin was extended so it could do arbitrary arithmetic or verify zero knowledge proofs or check Oracle signatures or, do various covenants, all the things that people want to extend Bitcoin with. If you were to try to use the Miniscript model to build complicated things with this, you would quickly run into trouble because the reasoning that you would need to do to convince yourself of the security and correctness of these things would become very large, and it would be quite difficult to manage. So as an example, on Liquid, we have a multi-asset blockchain, and we have a way to construct collateralized options. And so what an option is, what a call option is, for example, on-chain, is a mechanism where you can take a Bitcoin, and maybe you want to create a $50,000 Bitcoin call option using this. And so what that means is you're going to create the right, but not the obligation for somebody to buy the Bitcoin from you at $50,000 at some point in the future. And even though Bitcoin is worth much less than $50,000 right now, that option actually has value because maybe the price goes up to 100K, and then in the future somebody will get the 50K at a steal. So the way this is modeled on chain is that you take your Bitcoin, you lock it up in a script, and the script says the only way to move this Bitcoin is either to destroy the original option and cancel it, or the date written on the option goes by and nobody takes it, so then it expires and the money goes back to the original, or it gets exercised. So somebody can take it, but they have to put up the $50,000 and send it to me, or send it to whoever the counterparty winds up being after these things drift around the market for a while. And so you've got these three different endpoints, each of which is actually a collection of different conditions that have to be true about your script. And you have to argue that these things continue to be true no matter how the option moves around the blockchain, and no matter how the option tokens are issued and deissued and destroyed and so on. And you could convince yourself of the correctness of all this. And we pretty much have internally at Blockstream as we've tried to develop these kind of things. We've gotten pretty good at reasoning about all the things that we do with scripts. But then if you tweak something in this script, then it's hard to say which parts of your ad hoc reasoning continue to be true, right? Like there's a temptation to kind of say, well, we convinced ourselves this old thing was correct, and then we tweaked it just a little bit. So like probably that only changes our argument a bit. So it should still be good kind of thing. And after many iterations over the life cycle of any sort of software product, you're going to find that you've changed your stuff quite a bit, and the original reasoning for its correctness kind of becomes stale. And eventually you're going to trip up and you'll find that there's a bug and this is not correct or it's not secure. So with simplicity, you can instead take everything that you want to be true. You can write formally what you need to be true somehow in your proof system and then prove that it's correct. And now when you tweak your code, you rerun the proof verifier and it will tell you what things used to be true that are no longer true. And then you can go repair those specific parts of your proof, assuming they're repairable. And if not, then you've got a bug and your thing, great job, right? Your formal methods were able to save you. And so you can do this kind of mechanistic proving that a program written simplicity matches some sort of specification. And that's something that you can only do if you have a formal model. And this is really like the $1 million or $1 billion value proposition of simplicity, is that it's defined in such a way that simplicity is itself a formal model. It's not only a collection of code that runs on the blockchain and checks various conditions. It is a formal model that you can represent inside of a proving system, and you can get very high assurance of whatever properties of your contracts you want to be true. And that assurance will continue to hold even as you iterate on things, as long as you make sure that the machine checkable proofs continue to machine check.
In terms of formal verifications, is it the simplicity of simplicity that makes it different from other smart chains, other smart contracts and how they work on other chains?
That's one way to put it, right? So mathematically is very simple, right? So you have like the identity function that I mentioned. You can write that f of x equals x is your identity function, or the unit function, where that function is f of x equals 1. Where 1 is, it's not actually the number 1, it's some like special unit value. So it is simple in that sense. But where I think the real simplicity comes from, or the real ability to formalize, is simply the fact that these were defined in a way that had formalization in mind, where we were thinking, what is the mathematical structure of this? So EVM, as an example, which is the opcode language that's used in Ethereum, there are some things they did that are actually formalization, reasonably formalization friendly, where, for example, they'd have arithmetic using 256-bit numbers, where you can add two numbers, and if they overflow, it will wrap around, which is something you have to be aware of. But other than that, the addition and subtraction work exactly the way that you'd expect. But then there are other things in Ethereum that are very difficult to reason about. So for example, they have constructs that will allow you to call remotely into other code and then recursively call. So you have functions that can call themselves and call others. You have loops. You can construct programs in Ethereum that will loop, and where you can't tell a priori how many times they're going to loop. You set a limit, of course, your gas limit, so that will cap it. But if you loop more times than the gas limit, then your transaction will simply fail. And it's possible to construct programs in EVM where you simply can't guarantee that that's not going to happen. And in fact, it's difficult to construct programs in EVM where that can happen. So in simplicity, we defined every combinator with an eye towards being formalizable. We avoided having functions. And this is maybe kind of a surprising thing about simplicity, but we don't have functions that you can move around and manipulate. A simplicity program is itself a function, but the values that you manipulate are always values. And what that means is that the number of possibilities of these values can't grow dramatically faster than your program itself grows. So the more complicated a program you write, the more complicated the values you can work with. But in something like Ethereum or anything that has first-class functions, you can have a slightly more complicated program that all of a sudden goes from being tractable to reason about to completely intractable, or even literally impossible. You can create uncomputable or halting complete kind of constructions. So the other thing that simplicity does that makes it easier to reason about is it uses this combinator model rather than the opcode model. So in Bitcoin script, I mentioned you have the stack, right? And you've got all these blobs of data on the stack. You rearrange them, pop them, push them kind of thing. EVM doesn't use a stack. It uses a hash map, or it uses a map where you have kind of an arbitrary number of variables, and you have kind of every contract has this data store, and you can just write stuff and read stuff in arbitrary places. And in both cases, the way that your scripts work is you do one opcode after another. So you have this whole massive state of the blockchain and what's in your contracts, local memory, and so forth. And then every opcode manipulates that entire state in some way. And so you have this series of state manipulations. And this very quickly becomes difficult to wrap your head around and to reason about mechanically. Whereas simplicity, like Miniscript, tries to be very local in its reasoning. Your programs are structured as trees, where at the bottom you've got some combinator. In Miniscript is an and or an or. In simplicity, it's probably the composition combinator. And you can always look at subtrees of your program. So given a simplicity program, you can say, well, I've got the composition of this thing and of this thing. And I'm going to reason about this and try to make, come up with some provable statements and properties that hold about this, find some properties that need to hold about this. And then I'm going to prove that given two programs that have the properties that I care about, if they are composed with this particular combinator, then the composition will hold, but will have some other property, which is that the coins can't get stolen or something like that. So it's designed to be composable, to break apart in ways where kind of the default mode of constructing simplicity programs will lend itself towards this kind of analysis being tracked.
Can you talk about how simplicity would be able to offer CTV and APO functionality?
Sure. So simplicity in terms of expressivity goes much further than Bitcoin script and much further than much further than script in two ways. One is that you can express any kind of computation that you want in simplicity. So Bitcoin script is kind of dumb. You can only add numbers that are up to 32 bits in size, and there are additional limitations there. You have branches and stuff, but you can only do so many branches. You have no, really the arithmetic. Oh, and you have no ability to break down these stack elements. We don't have opcat or op substring. that would let you pull apart data or reconstruct it. So in Bitcoin script, there's just a lot of things you can't express for really just like accidental historical reasons, right? Like it wouldn't fundamentally change the way that Bitcoin works if you could add 64-bit numbers, but you can't. So Ethereum does a much better job of being more expressive in this way. Then the other way that simplicity goes further. So simplicity goes all the way, where you can, anything that is possible, any computation is possible to express, you can express it in simplicity. I believe the same is true for EVM. And in both cases, there's a caveat that, your transaction has to fit inside of a block kind of thing. So there are actually limits here. But in a hypothetical world where you had infinitely sized blocks and infinitely sized transactions, then you could express any computation. The other direction that simplicity extends things is by having what we call covenants, the ability to introspect properties of the transaction. So in a simplicity program or in an Ethereum contract, you can say, well, only I have, 10 BTC in this output. And at most 1 BTC is allowed to move in a given block or in a given day or something like that. Or you're allowed to move an unlimited amount to this address, but not to any other address. Or you're allowed to, there's a limit on your fee rate or a limit on your output unless this extra key signs, and then that limit is relaxed kind of thing. So you can look at where the money's going. It's not just like, once the coins are unlocked, once your policy is satisfied, then the coin is a free-for-all, is the way that Bitcoin works. With covenants, you can control not only under what conditions do the coins move, but where do they move given those conditions. So those two things together, arbitrary computations and transaction introspections, allow you to do pretty much anything that you would want to do on a blockchain. And in particular, they allow you to do things like any prev or op CTV or pretty much any proposal or op vault by James O'Byrne or any of the proposals that people have suggested to bring onto Bitcoin. You can implement those in simplicity because simplicity is expressive enough. And something that's cool about this is this dovetails quite nicely with what I was saying earlier about simplicity being kind of a specification language, of simplicity having a formal model. And that means that even if simplicity is not on Bitcoin, which it won't be, certainly this decade, hopefully it will next decade, but let's be optimistic, right?
Is it that far out? Is it because Christian said he thought maybe 10 years so it could be more than a decade?
It could, this decade is less than 10 years, right? But it could be, so getting things into Bitcoin is always very difficult. And simplicity is actually very big, despite the name, right? It's an entire replacement for the script interpreter. And there are a lot of design decisions in simplicity that are open to debate, right? Like one of the nice things about Taproot is because it was so small, we were forced into a bunch of design decisions so that there was less room for people to bike shed, how exactly we should have done this. Simplicity does everything. There are a lot of ways to do everything. So there will certainly be a lot of strong opinions about different trade-offs we can make and so on.
Yeah.
In addition to the usual consensus process and going through the QA and deploying this and all the difficult things. But even without simplicity on Bitcoin, simplicity has a role to play on Bitcoin because these other smaller incremental improvements that people talk about, like opcat or opvault or opctv or sighash APO, these can all be specified in simplicity. So rather than coming up with a proposal where you kind of write some pseudocode, you probably write some C++ code that you can merge into core, and you write some Python code that you can kind of use as pseudocode to illustrate what you're doing. You can write simplicity code. And then now, if somebody has a technical concern, this new proposal might enable some sort of horrible transaction structure or some sort of crisis, you can produce a proof in simplicity that will bound that. Hopefully you can prove that whatever someone's saying literally can't happen. That would be nice. But even if it is possible for your new opcode to be abused to cause bad transactions, you can come up with a proof that that can only happen under certain circumstances. Or you can say, well, I can prove that as long as a user stays within these guardrails, then they're not going to lose their funds kind of thing. And then maybe you actually want to build those guardrails in or not or whatever. But what's cool here is that because we have a machine checkable specification language in simplicity, we're able to make these kind of claims, and we're able to create like very rigid proofs, like solid proofs that are not really subject to debate. Or if they're subject to debate, it's a much more fruitful debate than the kind of like speculation and like, well, what if people do this kind of, and arguing about definitions that we see with a lot of other proposals.
There's been a lot of talk recently also about drive chains. Can you explain what drive chains are and how they're different than other layer twos, like, or how they're different from layer twos like Liquid or Lightning?
Sure. So in brief, the drive chains are a kind of a side chain, similar to Liquid, but not so similar to Lightning. So maybe, actually, let me start with Lightning and then try to move. So Lightning is a layer 2 where at the lowest level is kind of a layer 2 between two people. So you and I can open what's called a payment channel. And then we, by re-signing a single transaction between us, are able to shunt money between you and I. And then where the network part comes in is there's kind of this cool construction called an HTLC, which means that if you and I have a channel and then me and Chris have a channel over here, we're able to link those. So you can pay Chris by giving me money in a way where you can be assured that when we update our channel to give me money, at the same time, my channel with Chris will be updated. So the money's just going through me, minus a fee, perhaps. So you have these two-party channels and this ability to link the two-party channels. Liquid, so I guess in Lightning, there really isn't a change in the custody model, right? If you have coins in Lightning, they are still your coins. They may be tied up temporarily, and like you need a counterparty to sign off on movements, unless you want to exit, which has a delay and so on. But the coins never really leave your custody. So Liquid, to contrast, is a sidechain. And in Liquid, the idea is that you move your coins out of your own custody into custody of the chain. And on Liquid, the custody of the chain means they're actually in the custody of a quorum of what we call watchmen. These 15 different signers who all have Bitcoin keys, and any 11 of those 15 are able to sign to move the coins. And while your coins are in custody on the Bitcoin chain, while they're in custody of the watchman, then you kind of receive a token on the Liquid blockchain representing that. And then when you want to move back to Bitcoin, you destroy the token on Liquid. The watchman will sign a transaction to give it back to you. And so you're actually moving custody in and out. And this is all transparent. So in Liquid, you move the coins into custody of the blockchain, which means custody of the federation. And then when you want to move the coins out, you basically request to have your coins back, and the federation sign the transaction. So this is all transparent. You can see on the Liquid chain what coins are moving in and what coins are moving out. So if the federation is going to misbehave in some way, then that would be immediately noticed and presumably cause some sort of exodus and chaos. And these functionaries are known, at least to each other. So there would be legal action and so forth. But ultimately, you are actually moving the coins out of your own custody on the Bitcoin blockchain. And so in some sense, you can think of Liquid as being kind of like this giant multi-sig split custody wallet for all of the coins that are on the sidechain. And while the coins are on the sidechain is a completely independent blockchain. So there's this other set of functionaries. They're actually the same people, but conceptually they're different, called block signers. And the block signers sign blocks. So rather than having a proof of work, you have a blockchain that's extended by the block signers signing blocks. And on this chain, you have coins, which represent the Bitcoins that are custodied in the system, as well as other assets. And then it's we have all these other different rules. We have the kind of this free-for-all, because it's totally a separate blockchain. So we have confidential transactions on there. We have multiple assets on there that you can issue and deissue. You can create your own asset types and trade them and so forth. We have new script opcodes that allow you to do covenants. So Liquid has had covenants since it was launched in 2018 in some way, shape, or form. We will have Simplicity at some point. So we have all of these different extensions that we're able to deploy on Liquid, because Liquid is kind of a smaller network of participants where there's a higher barrier to entry than there is on Bitcoin. Like, we're able to require higher hardware requirements to use Liquid, for example. And we are able to make changes to Liquid without requiring, buy-in from like a million different industries and a million different participants kind of thing. So changes to Bitcoin are very hard. There are many different stakeholders with many different interests and so on. And in Liquid, everything's just just smaller, so we can do more stuff more quickly, and we can use it as more of a I don't want to say a playground, right? I mean, there's real money. It's a production grade system, but we can use it to deploy technology that would not be deployable, at least immediately, on Bitcoin, as well as technology like multiple assets that just on principle would never be on Bitcoin, right? Like no matter how rock solid we made the tech, the Bitcoin community would never accept Bitcoin being a multi-asset blockchain. And we would never push that, of course, but like that's the kind of thing we can do on Liquid because it's a different beast. Now, drive chains are also a sidechain. Now, unlike Liquid, when you move coins onto the drive chain, you, rather than having them be in custody and having all these block signers signing blocks, so basically you have a set of signers in Liquid moving everything forward, and everything kind of mechanically works because you have all these always online participants. In drive chains, you kind of reuse the Bitcoin blockchain. So the blockchain under drive chains would be merge mined with Bitcoin. So Bitcoin miners are going to mine the drive chain simultaneously with Bitcoin. And the way that coins move on and off is that you lock your coins on Bitcoin, and you would need some extra opcodes for this to work, but you lock your coins on Bitcoin. Then they become accessible on the drive chain, the blockchain. And then when you want to move your coins back, you destroy your coins on the drive chain thing, so similar to Liquid so far, and then you provide a proof on Bitcoin. So rather than requesting to the blocks, to the watchman, saying, hey, I burned my coins, give me my Bitcoins back, you provide a proof to the Bitcoin blockchain. And this proof looks at the drive chain and says like, okay, well, indeed, you burned these coins and they've been buried under 100 blocks kind of thing. So this proof is valid. So all right, the coins are destroyed. You can have them back on Bitcoin. And the economics of this are pretty radical, actually. Like this sounds mechanically like a pretty reasonable design, right? But the incentive structure here is really very different from the way things work on Liquid or the way things work on Bitcoin. And the reason is that with drive chains, if you make a proof and try to move your coins back onto Bitcoin, then the drive chain gets rewritten because some rogue miners decide to rewrite a bunch of blocks or something. Then the Bitcoin chain has already accepted your proof, right? But then the drive chain gets rewritten so that your proof is no longer on the chain. So now, after the chain's been rewritten, you have your coins in both places. So basically what's happened is you've made the drive chain insolvent. You managed to steal coins. And maybe more worrisome, even if you don't care about drive chains, there's kind of an incentive to do this. Like the more money goes onto the drive chain, the more value there is in miners trying to rewrite the chain and steal coins this way. So it creates something of a honeypot. And maybe worse, it creates an incentive for Bitcoin miners to misbehave and to try to rewrite Bitcoin blocks. And that's just a consequence of this merge mining structure. So the incentives here are very strange, right? And so the main guy driving this is this guy, Poelstra. He is an economist by trade or by study or something. And his reaction to these kind of weird incentive structures is to kind of lean into it and say, well, like that's how the world works, right? Like everything's is like interlocking incentive structures, and we can just like build enough technology so that we can build a world around any kind of incentive structure. And he's really struggled to get anybody from the Bitcoin community to agree with this way of looking at things, right? So the drive chains, as I see it, are really viewed with suspicion from the Bitcoin community as being like not really incentive compatible.
So as is everything.
Yeah, right. As is everything. I mean, Bitcoin itself is really on the edge of being incentive compatible, right? So you do anything to it, and then you've tipped it over.
And really, what's the upside? Because if the goal is to have multi-asset on Bitcoin, I mean, we can do that with Liquid already. So isn't that a better, safer way to do it?
Well, the upside is that you could argue in Liquid, you've got these 15 participants who have the ability to abscond with all the funds. And if drive chains, if you want to abscond with all the funds, you have to rewrite the chain a whole bunch, which is expensive. So there is an argument. So they're different trust models, right? And I agree with the intuition you're maybe getting at, that like the liquid trust model is probably a better trust model here. But it is quite different from Bitcoin, and it is a trust model in which you're assuming that 15 participants or 11 of 15 participants don't collude to run off with the coins, right? And that's very different from the trust model of Lightning, where there's really like no ability to steal anything, or the trust model of Bitcoin itself, where even more so, there's no ability to steal anything, at least unless you like rewrite thousands of blocks or as many blocks as you want to secure your coins by. You can wait that many blocks and then you have that much security.
Yeah, but isn't the answer to that is to increase the number of people that need to collude?
Mm-hmm. Yeah, so that's a fun direction to go in, right? Is to have these like massive mega federations. So imagine a liquid where we had like 110 out of 150, or like add a few more zeros to that.
Yeah, in different countries, in different languages, that just would be extremely unlikely to collude.
I think trust-wise, that's a great direction to go in, and I would certainly feel comfortable with that kind of model. Then you run into trade-offs, of course, where technically it's quite difficult to run a network that has this many participants who all need to be in sync all the time.
Right, for the same reasons. Yeah.
And maybe socially, it becomes harder to coordinate all these people to be running the same blockchain and agree on like when do we want to do upgrades and stuff like that. But yeah, certainly that would improve the trust model to just increase the numbers.
Okay, so at the beginning you touched on, I just gave a brief mention of Frost and Musig 2. Can you talk a little bit more about those? Maybe give a more detailed introduction and some color on what's going on there?
The idea behind Musig or Musig 2 is that you can have a single public key that represents a group of participants. And every member of this group of participants has their own key. But what you do in Musig is you combine them all into one key. So from the perspective of the blockchain and from the perspective of validators, there's just one key. And you can't tell whether this is a single key that represents one person or a single key that represents a group of signers. And the Musig 2 protocol allows all of these individual key holders together to interactively produce a single signature that is a valid signature on a transaction with the combined key. So this whole group of participants is able to act as a single signer. And the cool thing here is that each individual signer is able to retain their own key material. And they never, even when they're interacting with each other, they never reveal their own key material. So if any one signer doesn't like a transaction, they have veto power, basically. The policy this represents is every single one of these signers agrees on the transaction. And the cool thing here is that it either produces one signature or zero signatures, right? Like it either works or it doesn't. And so when you successfully sign, you get this scalability benefit and this privacy benefit together. And with Taproot, there's even a little bit more of a benefit, because in Taproot, if you can produce a single signature that authorizes this transaction, that's very cheap. And as soon as you need to go past a single signature, you need to introduce what's called a script spend. And there's just a bit of extra data that you got to throw on chain. And you wind up costing yourself like an extra 30 or 40 bytes or something. So the idea behind Musig is that you can take a single key and have it represent a group of people. Okay, and then there's an interactive protocol here that's actually surprisingly non-trivial. So I sort of casually said that like the individual signers retain their key material and like they can't like trick each other into giving things up. But when you create an interactive protocol, you've got to think what happens when signers lie to each other, or what happens when one signer sends some data to a participant and different data to the other participants, or what happens when a signer like does half the protocol and then like doesn't reply anymore, just like drops off. Or what if a signer just replies but like extremely slowly kind of thing? Or what if he replies so slowly that some participant thinks he dropped off but other ones don't? There's a million different failure modes here. With Musig 2, conveniently, if anything goes wrong, the signature doesn't show up. That's kind of like the nice thing about having this like all or nothing kind of model. So this leads me into Frost. And Frost is a threshold signature scheme. And in Frost, you have maybe like 10 participants, and now like any 5 of them or any 8 of them, or whatever parameters you want. If you have a quorum of them, they are able to kind of interactively fill in the gaps for the missing participants, and they're able to produce a single signature. So now, just like with Musig, you have one key, one signature, assuming everything works. But now the signature represents a quorum of people. So you have this quorum kind of policy. And what's cool is you can nest these, or at least we've been working very hard to make these nestable. So the individual keys in a frost can themselves be frost, or themselves be musigs. I know for musig we can do this. I'm not so sure about frost. And so you can have kind of these arbitrarily complicated policies, signing policies, that are all represented by a single key. And to produce a signature with a single key, everybody needs to do this interactive protocol in the background. But all of the complexity here is kind of offloaded to the signers themselves. And so the blockchain doesn't care about the complexity. So the blockchain just sees one key, one signature, and they can't tell if it's a normal single key wallet. They can't tell whether it's a 2 of 2 lightning channel. They can't tell if it's a 2 of 3 escrow. They can't tell if it's some like more complicated thing, is the idea behind Frost. But as you might imagine, the complexities of this interactive protocol are even worse for Frost than for Musig, right? In Musig, you kind of worry about all this kind of misbehavior. In Frost, you could imagine that you need 7 of 10 signers, but then you have an 8th signer shows up and just starts gripping things. And you still want the protocol to work, right? You want to make sure that even if you can't necessarily tell who's misbehaving, somehow you eventually figure it out and you're able to get, like, as long as you have 7 honest parties, you can somehow weed out all the dishonest ones and then produce a valid signature. And that's a lot of the work that we've been doing over the last year, 3-4 years, has been defining a protocol that's resilient to all these different failure modes.
Shifting gears again a little bit, we recently talked to the guys from ZeroSync, and we talked about zero knowledge proofs and the Blockstream Satellite, which I thought was pretty cool. Can you talk about how something like that would work, and what do you think of this proposition?
I think it's a really cool idea. How does it work? There's a lot of work to be done to make this pull together. But the idea is for a user is that rather than having an entire blockchain to download, so the idea when you sync up a Bitcoin node, what you're trying to do is figure out the current UTXO set, which is what coins are where, what coins belong to what addresses, basically. And the UTXO set is something like I don't know, it's like a few dozen gigabytes or something like that. It's certainly not small, but it's not extremely large. But in order to compute the UTXO set, you have to download every single transaction and every single block that ever happened in Bitcoin. And we have some like 700,000-800,000 blocks. And so the entire Bitcoin blockchain now totals the better part of a terabyte in order to download. So the idea behind ZeroSync is that you could take the UTXO set, which is like 10 gigs or something, and then the entire blockchain leading up to that, you replace it with a zero knowledge proof that there was a sequence of transactions that started from 0 and ended with this UTXO set. And the zero knowledge proof, rather than being, like 800 gigs or something, is on the order of like half a megabyte or a quarter of a megabyte, just incredibly small. Absolutely incredibly small. It would be, actually, if they were using Starks, it would be, I think, 120 to 150 kilobytes. So like really just unbelievably, like way smaller than even a single block. And verification time would be way smaller. It would be commensurate with, 100 kilobyte kind of thing. So to verify this, you're talking about taking, like tens of milliseconds kind of thing, like well under a second, versus verifying, the whole 800 gigabyte chain, which on a powerful processor is going to take you, like the better part of a day, just like continually churning your 8-core CPU for 6 or 8 hours to sync the entire blockchain. And that with, like years and years of optimization kind of thing. So you dramatically reduce the size and the verification burden needed to get you from 0 to the current UTXO set is the idea. And the difficulty there is kind of, I've touched on this when I was talking about simplicity, is that the actual rules of the Bitcoin blockchain are not super well defined. It's kind of a scary thing, actually, because everybody needs to agree on exactly the rules of the chain, like down to like the every bit, every byte, every decision needs to happen in sync. But the rules are defined by a pile of C++ code that's kind of evolved over the last 8 years. Mostly towards being maintainable and better defined and using modern idioms and stuff, but it's still like the rules are defined by the code. So if you want to prove that all these rules are obeyed, and zero knowledge. You need to somehow lift all the C++ code into a zero knowledge proof scheme and have the statements being proven in zero knowledge exactly match the rules of the blockchain. So as I understand it, the zero sync people are trying something much less ambitious, at least to start. Where rather than validating all of the rules and validating all of the scripts and all of the signatures and stuff, they're just trying to validate the UTXO updates, I think is what they're doing first. So you sort of assume that the transactions are valid. Assume that any transaction that makes it into the chain is valid, and then prove in zero knowledge that there was a sequence of transactions that were in the chain. And even that is actually, that's a much more well-defined, and it's not hard to specify this in zero knowledge, but doing so in a way where you could tractably produce a proof of so much data is a really ambitious, thing. So I wish all the best to this project. I think it's super cool, and I'm super excited to see it. But the technology that they're using arguably isn't here yet. They're really on the frontier of what's possible with these zero knowledge proof schemes.
And what is the idea there? How does that tie in with the satellite?
If you are syncing the Bitcoin blockchain from Blockstream Satellite, say, then you need to get all the blockchain data, as I've been saying. And if that's 800 gigabytes, you need to obtain 800 gigabytes of data from the Blockstream Satellite. And it's a bit less than that because we compress it and we do a certain thing where we replay the last 24 hours of blocks and so forth. And we try to structure this so that it's easy to, as easy as it can be to get all this data, but is nonetheless going to take you several days. I don't know the exact number, but at least several days, maybe more than a week, to obtain all of this data from the satellite link. Whereas if we had zero sync, then you would be able to download the entire block history in 100 kilobytes. So that's, you download that from the satellite in a second or less than a second. And then the actual UTXO set, if you wanted to download the whole thing, you could do that in a much faster way. But you might not even need to download the whole thing. If you only cared about the UTXOs that your wallet cared about, you might be able to download a proof that the specific UTXOs you care about are included in the chain, for example. So there's a lot of room to dramatically reduce the amount of data you care about. For an individual wallet user, you can convince yourself of the state of the chain with only a few hundred kilobytes of data instead of hundreds of gigabytes. A factor 1 million reduction in the amount of data that you need to obtain.
Huge applications there for redundancy and then for giving access to people in really remote areas. And then I guess you could have a hub and spoke structure as well, where you're using the satellite and then people with mobile devices are syncing up with the satellite. It seems super cool.
Yeah, it's a super cool feature. So I'm really hopeful that this stuff will start to come together. But I think this is a project to watch over the coming years, not the coming months.
Can you let us know what's been happening with development of Bulletproofs++ and where that's going?
Sure, yeah. So Bulletproofs++ is a new paper that is an improvement on our old Bulletproof protocol, which in turn is an improvement on our old Rangeproof protocol. So when Liquid launched, actually even much before Liquid, back in 2015 or so, when we first developed confidential transactions, we created a scheme called a rangeproof. So the idea behind confidential transactions is that rather than having amounts on your inputs and outputs, and you can kind of see where all the money's flowing, you have what are called Pedersen commitments. And these commitments, you prove in zero knowledge that they add to zero. So that each one commits to an actual value. So there's a real value on every input and output, but they're hidden, and you provide a zero knowledge proof that they all sum to zero. And this is pretty cool, but there's a trade-off here, which is that to produce this zero knowledge proof, you can't use integers. You have to use numbers modulo 2 to the 256, or modulo a prime number that's near that. And what that means is that your numbers wrap around. Okay, so if I give you two outputs that are very close to 2 to the 256, and then I add them together, or if I have a number that's very close to 2 to the 256, and then another number that pushes you over the edge, I add them together, they'll wrap around to zero. So I effectively have negative numbers, or I can make things cancel. So naively, if we were doing confidential transactions using these commitments with just a zero knowledge proof that things add to zero, I could do something like have a 1 Bitcoin input, and then I would have a 10 Bitcoin output and a negative 9 Bitcoin output. And together, right, it all adds up, right? Because 10 plus negative 9 equals 1. So it's all on the level. But then like the negative 9, 1, like, I throw away. So we don't want that to happen. So what we do is we prove that all of our numbers are between 0 and 2 to the 64. And 2 to the 64 is a very large number. It is something like, it's 4 billion squares, so 16 billion or so. But it's nonetheless much, much, much smaller than 2 to the 256. So no matter how many numbers between 0 and 2 to the 64 you add up, you're not going to get up to 2 to the 256 and wrap around. I guess you would have to add so many of them that they wouldn't fit into the universe, kind of thing. So we use what's called a range proof, which says we're in the range 0 to 2 to the 64. And we created and this is another kind of zero knowledge proof. We prove in zero knowledge that we're in the range, but nothing else. We developed a scheme in 2015, Greg Maxwell did, that at the time was the most efficient range proof in the literature that didn't have a trusted setup or any other weird crypto assumptions, which is funny because this wasn't that long ago, but these are just like horrifically inefficient. These 64-bit range proofs are like 4 kilobytes. And for context, a normal transaction output is like a public key and an amount is like 40 bytes of data. So we're adding 4,000 bytes to a 40-byte object. We wind up, like certainly 100xing the size of our outputs, but 10xing the whole transaction, right? Like even when you amortize it across the whole transaction is pretty rough. So we developed this scheme called Bulletproofs a few years later. To use largely our friends at Stanford, Dan Boneh and Benedict Moons, and John Boodle at University College London. We developed this new scheme called Bulletproofs. And now instead of being 4 kilobytes, 4,000 bytes, now the size is around 600 bytes. So like a tremendous improvement, like a 5x improvement in the total size of these things. And it was also roughly twice as fast to validate. And then a few years later, some researchers developed a new scheme called Bulletproofs Plus that was a little bit smaller and a little bit faster. And honestly, we didn't read the paper. Like we were going to, and we probably still would. But before we got around to it, this guy, Liam Egan, showed up and he developed this new paper called Bulletproofs Plus Plus. Okay, so he combined all of this. And the benefits of Bulletproofs Plus Plus are not only is it smaller and faster, so our 600 byte thing is now like 450 bytes or something. Like it's really small, as well as being faster. But it's also possible to combine proofs across a whole transaction. And this is possible, we call this aggregation. This is possible with the original Bulletproofs, but only if you had the same asset for all your outputs. So as soon as we introduced assets, like it broke this aggregation feature of Bulletproofs Plus Plus. So you couldn't, so we had these nice 600 byte proofs, but you needed a new one for every output. With Bulletproofs Plus Plus, we can combine them across an entire transaction with all of the assets, no matter how many different assets there are. So you could have a giant transaction that has 10 inputs and 10 outputs and like 5 assets that are like all being mixed and matched and so forth. And you attach a single proof to this transaction, which is 500 or 600 bytes in size, and which takes just a couple milliseconds to verify, versus the old Bulletproofs, which take 4 or 5 milliseconds per output kind of thing. And the original range proofs were 4 or 5 milliseconds. Bulletproofs were 2.5, and then Bulletproofs are a little smaller. But the big thing is that Bulletproofs are now per transaction instead of per output, which is a cool thing. And so this is what Bulletproofs are. And when Liam joined our team, Bulletproofs existed basically as a paper that Liam had written that was not a super well-structured paper. It was like a whole pile of neat mathematical tricks that we were able to combine. And so what happened was we brought Liam onto the team, and then Liam and Sanket and Elliot Jin, who worked with us, and a few other people came together, and we just kind of did like a series of sprints. So the first one, we actually brought some, oops, my battery's just low, but that's fine. And so unfortunately they're all gone now, but you can sort of see behind me, there's a blackboard there. And so I actually brought Liam to my house, and we had this giant wall blackboard there, and we filled it up. But now it's erased. There's other unrelated stuff there, which is less exciting. So we spent a weekend just like with Liam, just like doing this crash course, and Liam kind of convinced us that all these crazy mathematical tricks actually worked. And then we did some similar crash courses between Liam and Tim and Jonas and so forth. And we spent a lot of time cleaning up the paper, tightening up the proofs in the paper and the arguments, in tightening them up, we actually found like a serious problem that would have been a soundness issue. So it's good that we went through this exercise of verifying the proofs. We were able to patch that up, and now everything's good now. We've been working on simplifying the paper. We've been working on implementing things. So we have SamKit has written an implementation of Bulletproofs++ in Rust, as well as one in C. So the Rust one we kind of use as a reference, and we're able to update that and iterate very quickly, because Rust is a very expressive language that lets you kind of express mathematical abstractions reasonably well. C is not. C is very difficult. Like as soon as you change your mathematical abstractions, you have to like rewrite half your C code all the time, because it's just such a rigid and unfortunately structured language. So we've been working on, we've been continuing to work on getting the paper together, which we tried to submit earlier. We weren't really thrilled with the state of the paper, and it turned out the peer reviewers were not either, unfortunately. So it wasn't accepted. But I think we're going to resubmit later this year, I think in October, although I forget to which conference. Cleaning up the paper, getting the 2 implementations in order, working on, as part of our efforts to clean up the paper, we've been able to kind of move away from having range proofs as a particular kind of zero knowledge proof to doing arbitrary zero knowledge proofs. So Bulletproofs could always do arbitrary zero knowledge proofs. Bulletproofs++ could always do arbitrary zero knowledge proofs. But in the early days, we would think of the general, like proving a random program is correct kind of thing as this big general kind of scary thing. And range proofs were this like smaller thing that we would just focus on, because range proofs are a much simpler thing to prove. With our new Bulletproof++ architecture, they're one and the same. The range proofs really are just a special case of the general thing. So while we're working on range proofs, we're simultaneously working on general purpose zero knowledge proofs. So we have a project to make our zero knowledge proofs, the way that we encode these programs as sequences of polynomials. We want that to be compatible with other zero knowledge proofs that are in the literature and that are deployed on various blockchains and so forth. So we've got a lot of work cut out for us. Finishing the paper, writing a specification for proving and verifying things, doing general zero knowledge proofs, including encoding these programs, getting the paper accepted, getting our code, like going through all the code review and QA and writing tests and everything, and getting our multiple implementations in sync. And then in the end, we'll have something where we'll probably be in a state where we could deploy on Liquid. And unfortunately, replacing our range proof code is a hard fork to Liquid. Like it's going to be like a flag data. It's going to be quite a difficult deployment. So we're pretty apprehensive. We're not super close to that. So it's an abstract kind of apprehension. But at some point, we're going to have to really kind of bite the bullet and figure out how do we want to do that deployment. And one further complicating factor is that the way that we do assets in Liquid today is not compatible with the way we do assets in Bulletproofs++. And initially we thought this was just like a no-go. We like wouldn't be able to square this. And then Liam came up with a way where we can do a conversion. So there's another kind of zero knowledge proof that we have to deploy on the blockchain, where you prove in zero knowledge that an asset represented in the old format is equivalent to an asset represented in the new format. And you're thereby able to port your old assets without revealing what they are. You stay in zero knowledge the whole time. You port your old assets from the old regime to the new regime, and then you can transfer to Bulletproofs that way. So that's one direction for Bulletproofs. The other direction we're going, which we feel much more confident about deploying, is trying to implement a Bulletproof++ verifier in Simplicity and saying, well, if we can get Simplicity into Liquid, that's a soft fork, that's kind of self-contained, that's something that we can manage. Then if we can write a Bulletproof++ verifier in Simplicity, which is hard, but it might be harder than coordinating a hard fork and having all this like crazy conversion stuff, then we could start to go in a different direction, where rather than thinking about the range proofs and the commitments on chain and stuff, we'll try to think about just arbitrary zero knowledge proofs, like the kind of like the options that I talked about and other financial derivatives and vaults and like Miniscript things. What if we could hide the exact policies that we're using on Liquid? So we're no longer revealing all of our code all the time. What if all of the transfers on Liquid were happening in zero knowledge, so that every basically every transfer looks the same. So we get this the usual privacy and scalability because we're not revealing our exact scripts. We're just providing a zero knowledge proof that the scripts are satisfied. And we get privacy and scalability basically. And then the result is a blockchain where a fungibility, that was the third word that I'm looking for, is that you look at all the coins on Liquid and they all kind of came, but you can't really tell the history of them, and you can't like mark certain coins as being worth more or less than others, which is as soon as you start doing that, your currency is dead, and we've spent there's a long, huge subfield of the history of money and the history of monetary policies and just keeping money fungible when various parties are always trying to market and taint it in various ways. So.
Yeah, I mean, so much of what you guys are working on is kind of really long time horizon projects. What excites you most about Bitcoin development over the next 12 or maybe 18 months?
So right now, I think the biggest problem, the most short-term problem, the most important immediate-term problem in Bitcoin is custody, is usability, user experience for storing your own coins. And there are two projects that I'm working on that I think are improving that story. One is Miniscript, which lets you create policies where you have certain keys, and then after a time lock, different keys become active and so on. And I'm really happy to see companies like Liana coming up. So Liana does like estate planning. They will provide phone support and stuff and help you set up this thing and help you store your keys and like write documents so you can hand off stuff so that when you die, maybe your keys go away, but then the backup keys become active and those are accessible to your estate lawyer or whoever they need to be accessible to. Then the other piece of that, of course, is this book, Codex32, where you can do Shamir secret sharing and checksumming, where you can have your secrets stored in these steel tubes. And rather than having your backups or whatever in these tubes where they sit somewhere and you never touch them, and then you try to pull them out in 50 years and hope that they're intact and nothing awful has happened to them. With the worksheets in this book, you can pull these out every year. You can come up with kind of a ritual where every year or however often you want to do this, you take your seed data out, you fill out one of these checksum worksheets, and if the checksum worksheet passes, you know that your data is intact. You know that like you didn't accidentally put the tiles in the wrong order, or none of them degraded, or like if there was some sort of natural disaster, they didn't get flattened out or anything crazy. Or you could imagine that you just like misplace the tube and then you find the tube eventually and then you're like, okay, I want to check on this, who knows where it was. Or if you died and the tube wound up at your lawyer's office for 18 months and then eventually got to the right place. There's all these things you want to do to check the integrity. And you probably don't want to have to load all the tube data into a hardware wallet every time you do this. Because if you're loading your data, if you're restoring your backup every single year, then eventually, over the years and decades, you're going to have a hardware wallet that's broken in some way. It's just like the law of large numbers, right? Because like this Jade is not going to last for 50 years, say. I'd be impressed if it lasts for 10 years kind of thing, right? Like you do have to cycle through these things. But with the paper worksheets, you don't have to worry that all of your hardware wallets are deleting the data they say they're deleting, that they're not leaking data when they say they're not leaking data. Your secret data stays on these worksheets, right? So you have this nice single page worksheet. Let me find this guy here. You tear this out. These are all perforated pages, but I don't want to rip this one out, even though I've got another 100. You fill out all your secret data. You tear out the page. If you tear out the page first, you write on a hard surface. Fill the secret data and you destroy it. And you know that your secret data is only on this page and nowhere else other than the tube itself. And destroying paper is something that is very easy to do in a way where you can have very high assurance that it is actually destroyed. And I've had a lot of fun experimenting with various ways. And I found actually the most reliable thing is to put the piece of paper in your blender with like a cup of water. And it just turns it into this gray goop that you definitely can't read anything. And in our earlier experiments, we were trying to burn it in various ways. And surprisingly, like aside from the safety issues, it's actually very hard to burn paper, or very easy to burn paper in a way where you can still read it, right? If you just have a single sheet of paper and you set fire to it, you can turn the whole paper black, but you'll be able to see pencil marks at the right angle. So if you want to burn it, like you need to totally turn it to ash and like really smash it up. And so you pretty much need like a wood fireplace that you put it in with a whole bunch of other material kind of thing. And then of course there's safety issue that I'm hesitant to recommend to a bunch of Bitcoiners living in high-rise apartments that they be setting fire to pieces of paper.
What could go wrong? Yeah.
Exactly right.
Well, that's very cool. I'm excited to go out and to get the book and take a look. Where can people go to find out more about Blockstream Research?
Sure. So we have a Twitter account, which is at BLK Research on X or Twitter, whatever you want to call it. We have a website, which I think is blockstream.com/research, but you might want to edit that to find the real URL. We publish a blog post on the Blockstream blog, just the public Blockstream blog. We publish a lot from research. We have a GitHub account, github.com/Blockstream Research. And in particular, GitHub/Blockstream Research/Codex32 is where you can download the open source copy of this book and see the source code and get new copies of the worksheets and print new copies of the paper computers and stuff. Because while I encourage you to buy one of these beautifully bound books, once you get it, you're not going to want to rip it apart. You're going to want to just print your own and then keep the book.
Yeah, no, it's very cool. Yeah, go buy two. Yeah. Well, Andrew, I really appreciate your time today. This is we spent a lot of time and learned a lot. So that's really appreciate it. And I look forward to having you on again in a couple of months.
Yeah, thanks a ton, Jesse. It was a lot of fun.